different models independently trained, then it's not a great idea. But if these models are actually like time related based on them being like different snapshots or earlier snapshots, then it usually works pretty well.
Okay. And also for you say dropout is behaving like a boosting. Oh no, the bagging.
Yeah.
Right. So like in bagging we have like parallel training, but
Yeah, that's right.
in dropout we do it sequentially.
So you can, okay, yeah, that's right. So you can think of dropout. So what I said was a crude approximation. I'm saying that it's an implicit way to do bagging without actually constructing different versions, because you can think of your minute batches as being like samples being trained in
Yeah,
parallel.
I get that, but I just feel like it's more behaving like a boosting because like every time you look at the error from the previous one, and then you like you drop out at the next iteration.
Oh, that's true. But it's not like you're actually looking at where the model's going wrong and training the model on where it's going wrong. You're just doing it in like a stochastic averaging that you're introducing every time during your call passing your model. So I think the connection to boosting is probably like less compared to connection to bagging. But you're right, it's best out of the distance to somebody introducing model on averaging.
And like you also say that at test time we don't do dropout, and I still don't get it.
Yeah, because at test time you want your models to be to be deterministic, right? Dropout is a stochastic noise, so and therefore if you want to have a model deterministic, then you want to make sure that the uh, the predictions are like whatever. If you feed in the same input hundreds of times, you want to get the same output. So if you drop out at this time, the mass that you create is going to be different.
I have a question. For the exponential moving average, do we just do entry-wise exponential moving average or for all the model parameters, or is it like, is there like a smarter way to do it?
No, it's just simple exponential movement. It's just for every single parameter, you just have this momentum update on itself, and then you just when you do the model snapshotting, you snapshot both the current model's value as well as the value of the moving averages. So at this time, you can use the moving average snapshot instead of the actual model snapshot.
And also another question is on point tuning. For point tuning, you have like different learning rate for different depth, so to speak.
Yeah.
And then what's the reason behind it?
Oh, the reason behind it is that the initial layers of the model are going to learn something more general, and so you don't want to retrain everything. And the other reason is that sometimes your downstream task might have not enough data, and therefore your models are like training all the way from scratch make your models overfit. Whereas if you retrain them prior from a much larger data set that you're trained on, it's likely to be more general and reusable for any custom task.
And one last question.
Yeah.
Will you come on Friday for the discussion?
Yeah, I will be coming. I missed it last week because of the deadline that I had. But yeah, it will be there.
Alright, thank you so much.
And I have a question about this file. So why when we have 1/100 deviation, when we have extra?
Yeah, so it's not about 1/standard deviation. The intention is to say that you multiply by 1/standard deviation in batch count, and dropout you multiply by some Bernoulli noise, right?
Right.
So you can think of both dropout and batch count using a multiplicative method.
Oh, because you are both multiplying.
Yeah, so the standard deviation that you multiply by in batch count is going to be very different for every single false task.
Right.
And similarly, the multiplicative Bernoulli noise will be infused in your
下周2日考场开始写，下周2日。
All right, so one quick announcement before we get started. So some people have been asking on Piazza about grades, and it will take a little while to get through even grading of homework 1 because we have to read your submissions in addition to running them, or I should say the TAs have to do that. So, and they're in the middle of it. But I think so far they Alex has gotten through all the performance analysis on them.
Yeah, we do have a grade distribution for the performance part of the rubric, and I'm going to be putting those into submission comments probably like in the next hour.
In the next hour, okay. So we can't give you complete feedback, but what we can do is say if you were kind of way at the bottom of the distribution in terms of getting the code to run efficiently, and then you'll get a comment back in B courses from if you're trying to decide whether to stay in the course.
It looked like a B- or below.
Yeah, so we're telling people who are headed towards a B- or below, keeping in mind that your grade might actually be higher in the homework than we're saying right now. If, for example, you didn't do very well in the performance, but you had a great write-up, so we haven't graded all the write-ups. So anyway, that's as much feedback as we can give you, because I know people did want to get some feedback on that before drop date. Any questions about that or any of the other course logistics or anything? Hopefully all of you have your NERSC accounts. I have to say we've been getting a little worried about people who keep getting their NERSC accounts turned on in recent days. But if you don't have a NERSC account, you should be very concerned and go talk to one of the GSIs about what's going on there. Okay, so this is, I think, one of the most fun lectures to give in the entire semester. So I'm really glad that I get to give it because there's very cool algorithms in here. And we're going to talk about data parallelism. And the first thing you should learn is that data parallelism is beautiful. It has really beautiful algorithms that come with it. And unfortunately, it's pretty hard to automatically map those parallel algorithms onto real hardware that we have today. So it can inspire you in terms of coming up with a clever algorithm, but you won't be able to exactly write in these algorithms and have it automatically turn into things that are going to run well on machines like Cori. And a lot of the the programming models that you're going to see in the course are going to have some features of data parallelism. It'll come up in GPUs, which John Owens from UC Davis, who's an expert on GPUs, is going to be lecturing about on Thursday. It will come up, I think it's next week or the week after, when Aiden talks about MPI and the collective communication part of message passing MPI. It comes up in the MapReduce model in cloud computing like Hadoop and Spark. So, and I'll refer to some of those things a little bit as forward pointers today. So there's also some surprising things, and that's kind of the main thing about this, is to understand these are non-obvious parallel algorithms, whereas a lot of the things that Jim talked about last week in terms of how do you decompose a physical domain into pieces and then parallelize that algorithm, some of those are pretty straightforward in terms of how you decompose them. He talked about things like doing reductions, and those will come up again here, I think. And so these will be useful. And I guess one quote that I like is every non-trivial parallel algorithm uses a prefix scan. So we're going to be talking about prefix scans and what that means. This is a quote due to Alan Edelman, who was a postdoc here many years ago and is now in the faculty at MIT. Okay, so our cartoon of machines, you've seen this before. We have our shared memory machines. You're working hopefully on OpenMP programming, and you've seen what it's like to have a bunch of threads that are all accessing shared memory. The next model that you'll be working with is GPUs, which will be a little bit closer to the data parallel model. And then after that, you'll be doing MPI, which will be in the distributed memory model in the middle there. Today we're going to look at a parallel machine model, an abstract machine model that we call a single instruction multiple data, or SIMD model. You've heard that today. You've seen that in homework 1 because you heard about the SIMD instructions. But originally this was a model for building large-scale parallel machines. And so that's going to be kind of the intuition behind what we're thinking about here in terms of parallelism. And the thing we'll worry about in terms of the ideal cost model, and this is where it becomes unrealistic, is let's assume there's an unbounded number of processors or arithmetic units. So we're going to do things like with just crazy numbers of processors and try to figure out how fast we can make parallel algorithms run that have those kinds of processors. And then we'll talk about how it actually maps onto useful parallel machines. Okay, so we're going to start with some really simple things. So what are you doing in general in a data parallel model? You're doing the same thing on every processor. So that's one of the key pieces of a data parallelism, is they don't do different things. They all do the same thing, but they can do it on different data elements. So for example, if you just have a unary operator f, let's say you want to square the elements of square a scalar value. It just takes in one argument. Then you can do a data parallel operation on it, which is taking an array A and producing an array B, which is the square of all the elements in array A. Okay, and you should get some idea that this is something you can do very quickly in parallel. If we've got an unlimited number of processors, we can put a processor at every one of those elements of A, and we can get that operation to run in constant time. So in constant time, you can square all the elements of an array, independently of how large the array is if we've got an unbounded number of processors. Now similarly, if we've got simple binary operators, like we want to add two arrays together, we'll just do pairwise addition of the array elements, so we can also do that. It's going to be easy to parallelize. And that might look like some code in a language that you might see in something like MATLAB, or languages, if you go back in history, APL, and there are other data parallel languages that have been around that do this. Nestle is one of them that I'll mention later, and high performance Fortran as well. Okay, you can also take a scalar value, so say an integer, and assign it to an array, and that will have the effect of broadcasting that integer out to the array. So in this case, we just say B is equal to A, and I'm using B for the uppercase for the arrays and lowercase for the scalars, and that will broadcast the 3 out to all the elements of the array. And that's going to be useful for a lot of things that we do in linear algebra, and comes up in other, and a lot of the scientific calculations and other things that you do in machine learning and so on. So this is an AXP, or also called a SAXP for single precision, or a DAXP for double precision, so A, X plus Y. And there's the formula for it. And you can see that if we want to do that, we basically are broadcasting the A out across X, so that we can do a multiply of that, the number 2 times everything that's in X, and then adding it to Y to get the result Z. Okay, So now, in addition to having those basic massively parallel now array operations that can do computation on arrays, we also have the ability to do memory operations on arrays. And so some of these will look like assignment statements, and I've just written a little bit of pseudocode here. So we've got 3 arrays, A, B, and C, that are all double precision arrays. So think of those double precision floating point. They're little tiny ones so that we can kind of think about some simple examples here. So they've each got 5 elements in them. And the array B has the elements 0 through 4.4 that you can see there, the floating point values. X is an integer array that we're going to see in a minute how to use that. So the first thing we can do is just in a simple assignment that copies the array B onto the array A. So we can just write that as A equal to B. We can also use a stride. And so sometimes we'll call this a strided memory operation. This comes up in data parallel operations, but we're going to also see it in other kind of I/O settings. People who have studied network stuff may see it in RDMA features inside of a network, but the question that what happens in this case is, let's say we want to copy the elements of B onto A, but only with stride 2. So we're going to take every other element of the B array and copy that onto A. Notice that that's going to be smaller than the array A, so it's only going to copy over on top of a subset of the array A. Exactly what the rules are for copying, large arrays onto small arrays or small arrays onto large arrays will depend on a particular programming language or programming environment, whether they have to be exactly the same size and the same shape, or whether it will do something kind of automatic for you. But here I'm saying, well, in general, we can copy a smaller thing onto a bigger thing, and there's plenty of space. We can also do something like copy a column of a 2-dimensional array like C. So C is a 5x5 matrix, and we can copy just a column of that, which would also happen if it were a row major layout, which would be a strided memory operation. And so you see these kinds of things in MATLAB all the time, but you can do them in a data parallel model. But you do need to think about, as you're thinking about sort of, if you start worrying about data movement, that is very different to copy something that's contiguous in memory versus something that is laid out in a strided fashion, because of the way the memory system, as you know from homework 1, will not perform as well if you're not accessing contiguous elements. And then perhaps the most powerful are the gather and scatter operations. So this you take an indexed array, so this is an array of integers, and I'm using here an example in which there's just a permutation of the integers 0 through 4. So we've got exactly one element so that all the shapes will work out. And I can use that on the right-hand side, which would be called a gather operation. That's kind of rearranging the elements of the right-hand side to gather them into an order that I want to see them in. So it's going to move, when you do the assignment, then it's going to move them by taking the index value, say 3, and looking up what is the value of B at index 3. Well, it's 3.3, so that's what gets written in the first location. And a scatter, on the other hand, is where I write it out in a kind of arbitrary order. So gather is reading it in an arbitrary order, but writing it contiguously, and a scatter is reading it contiguously, but then writing it in an arbitrary order. Questions? Okay. So the other thing that will come up in our data parallel algorithms is masks. So although you can't, in a pure data parallel model, all the processors have to be doing exactly the same thing at every step. And by the way, I should say that a lot of people use the term data parallel in a much looser way than I'm using in this lecture. I'm using it what we would call a pure data parallel way, where all the processors have to do the same thing. And sometimes people will use it meaning, oh, they're all working on different pieces of data, but they're doing somewhat unrelated things. So here they can't do anything different, except you can turn some of the processors off. And you do that with a mask. So in our kind of virtual machine where we've got unlimited numbers of processors, and we put a processor at every one of those locations, if we have a mask, which you can specify here as a true-false array or something, or as ones and zeros as it's shown here, then under that mask, the only things that will be added between A and B, so we're adding A and B together, but under this mask, so only the, when we say A is equal to A plus B, under M, then only the places where there's ones do you get an updated value of the matrix A, array A. Okay? And I'm going to talk we're going to talk about segmented scans, which are another idea that will be important in the algorithms. We'll do that a little bit later after we, well, actually in a minute. Okay, so reductions. So we talked about broadcast. So broadcast is take a scalar value and send it out to all the elements of the array. A reduction is the opposite, which take all the elements of the array and turn it into a scalar value using some kind of a binary operator, such as plus or times or min or max or whatever. And so we take our array A, and we can compute the sum of the array A just by saying do a sum reduction on it. Okay, and so what we're going to require in order to do this in parallel efficiently, and we'll talk about specific mappings of it in a minute, is we'll require associativity. And why do we want to do that? Because we want to independently be able to compute the sum of the, say, the right-hand half of the array from the left-hand half. And if we can't assume associativity, we're going to get a different answer if we do the plus operations in different orders. So, fortunately, plus is associative, so we can rearrange the parentheses in that and add up the right-hand side separately from the left-hand side, and then add the results together and get the same answer, at least if we're doing integer arithmetic. This is, of course, useful for things like dot products, where we're computing the sum of a times y, x times y. So we're just doing the pairwise multiplications and then adding the results together. So you can get a nice dot product here, and there's the intermediate value of the products, and then the sum. Okay, so slightly more general than a reduction is a scan, which does the reduction type of operation, but will also leave partial results in each one of the array elements. So you don't get just a single value out, you get an array of the same size as the input array out of the result of the scan. So for example, if we do a sum scan on this array of integers A, what do we get? Well, we get in the first location just a 3, and then we get the sum of the first two elements 4, and the sum of the first 3 elements 5, and so on all the way through the array. So now that's a sum scan where we're going through, and this is called an inclusive one because we're including the element at that location in the scan, and I'll say more about that in a minute. We can also do a scan on other kinds of operations. Similar to reductions, we can do things that are associative. So we could do a max scan, for example, and you can see how a max scan is going to vary throughout the array. It's going to say, well, here's there's a 3, that's the maximum value up until I get to the point where there's a 4, and then that's the maximum value all the way through to the end. That would be a max scan. Okay. Questions? Yes?
How do you parallel sum scan?
Yeah, we'll talk about how you parallelize sum scan. It's a very good question, and it's not at all obvious. So, okay, so there's 2 different kinds of scans that I mentioned, and we're going to next talk about, after I talk about these for a minute, we'll talk about hardware and then how you parallelize these things. But there's an inclusive scan, which is where I include the ith element in the ith operation. So it starts with A0, and then A1, say A0 plus A1, A0 plus A1 up to AN minus 1, the last element, and so on. Sorry. An exclusive scan doesn't include x sub I when it's computing the output in the ith element of the output array. So that means you need some kind of an identity value to put in the first location because you're not including any elements in there. So there we've just written it as an identity. So for example, if we're doing a sum scan, we would put a 0 in that place. If we're doing a multiplication scan, we would put a 1 in that place, and so on. And then but then it has the same sort of definition, other than everything is kind of shifted over by 1 because you're not including the value at that position. And you can actually go back and forth between these a little bit. So the inclusive version you can get from the exclusive version by applying by taking the output of the exclusive version and adding the original input to it, right? That will give you the value that you get from the inclusive version. So it'll just add on all the elements of the original array. If you try to go in the other direction, you need some way of doing an inverse. So for example, if you're doing a sum scan and you've got an inclusive thing, it's got say the first value of the element in that array, you have to be able to do a subtraction. So that means you need an inverse operation for whatever it is, whatever is the binary operator that you're doing the scan on. But you can also do conversions between these if you've got shift left and shift right sort of operations in your arrays, which are other primitives that often come up in data parallel languages that I haven't explicitly mentioned, but that you can imagine they're a little bit more expensive to implement because you've got to move data around, but you can certainly do those kind of shift operations. Okay, let's talk about our ideal hardware model, and I talk about this partly because systems actually did at one point look like this, and some of the classic papers on this are referring to these kinds of machines, such as the Connection Machine 2, CM2, and the Mass Power Machine. So these were big SIMD machines that were some of the fastest machines in the world, near the top of the top 500 list and so on, and the idea was that they had a large number of really tiny processors. So there was sorry, and they were tiny in the sense that that they don't actually do any control. So remember, the processors all have to do the same thing at the same time, so they don't need any logic in there or control logic to decide whether to branch or whatever. Instead, there's just one control processor that says, okay, everybody do a plus, and the only thing that can cause branching and stuff is it can sometimes mask some of the processors out and say if some of the processors turn off, everybody else do a plus. And so this is a fairly different model than what we see in hardware today, but is the inspiration behind these data parallel algorithms, and as I said, was behind these machines in this one era of SIMD machines. And so the ideal cost model, again, what I mentioned earlier, is there's an unbounded number of processors. Now, obviously, on any one of these machines, there isn't an unbounded number of processors, but typically, it's a very large number of processors, and so that is going to large enough that you might think about having a processor at every element or just a small number of elements. We don't worry about the control overhead, and we don't worry about communication. In this idealized world, we're just going to talk about how many steps does it take to execute a parallel algorithm on one of these machines with unbounded number of processors. And that's often called the span of the algorithm, the parallel span, which is kind of on the best case with all the processors that you can have, how long is it going to take to compute that. And in a data parallel machine, it may be a little bit different. That span means all the processors are doing the same thing at every step. And we'll sometimes refer to that as T infinity. So what is the time on an infinite number of processors? And that'll give us a lower bound on how fast things can run on a real machine. So it is useful when you're doing algorithm analysis. Okay, so what's the cost of doing just a simple array addition? Well, the cost is a constant time because we've got an unbounded number of processors. We just put one processor at each element of those pairs of elements of arrays A, B, and C, or triples, and so you can each processor can just add up its two elements and put them into the result matrix, result array C. And even if they're not aligned, there might be some communication between the processors, but we wouldn't really worry about that in the cost model. The cost model just says, well, I can take these two arrays and add them together. And then what about reductions and broadcasts? Well, the cost for doing one of these kinds of operations is going to be log n, and we'll just use a tree of processors. Okay, so this is now in the case where we have an unlimited number of processors. It's going to turn into a log n computation. I think it's pretty straightforward to think about this, but if we're doing a broadcast, one processor will send to two processors, and those two processors will send to two processors, and so on, or whatever number you want for your base of your log. But that will give you a broadcast time of log n, and where n is the size of the array. On the other hand, a reduction, or we want to say add things together, can also be done in log n time, but we're going to then have, say, two processors get together and one of them will add the two results that they both own, and then they will combine together with another processor to get the results, and so on. So you can think of there being a processor at every one of these internal nodes of this tree, and that will give you the log n time for a reduction. Okay, so associativity is pretty important here, and we have, just looking at this tree and the reduction, we are adding this part of the tree together before, and this part of the tree together, sorry, the numbers are slid over a little bit here in the way the PowerPoint formatted, but we are going to add them in a different order than if we were writing a serial code, which would just add 1 plus 3 and then plus 1 and plus 0 and so on. And so it is going to give you, it'll give you the same answer in integer arithmetic. So is it okay to use these reductions on floating point values? Well, neither plus nor times are actually associative in floating point arithmetic. They're not. They are in real numbers, right? In real arithmetic, but we don't have real numbers with unbounded precision on a computer. So we've got floating point numbers, and they're going to round somewhat differently depending on the order in which you do those operations. So, for example, I mean, just to give you kind of extreme, assume you've got the expression, 1 plus 10 to the 20th plus minus 10 to the 20th. So there's just those 3 terms that you're adding there together, and if you associate it on the right, clearly the answer is going to be 1. If you associate it on the left, you'd lose the 1, and then you might end up with 0. So you're going to get a different result depending on how things round. So you don't get the same answer, but and you may get, in different implementations, depending on how that tree gets mapped onto the processors, you may actually get a different, you can get a different value every time you run the code. I think the libraries will try to give you at least the same answer if you run it on the same machine, on the same configuration, on the same number of processors, but if you run it on a different number of processors, you can imagine the association order is going to be different, because you'll have, let's say if you have only 2 processors, you'll have the left part of the tree and the right part of the tree. If you have 4 processors, you're going to have 4 chunks, and the associativity will be different, so you'll get different answers. It's often okay in a lot of floating point algorithms to go ahead and use this type of associativity, but you do need to be aware of it, and if you're developing numerical algorithms, to think about whether or not it's okay to do this, and you should be aware of the fact that you're not going to get exactly the same answer. And I think you saw this even in homework 1, where people were getting slightly different answers. We allowed slightly different answers. We didn't allow completely different answers, because that meant there was something else going on other than just the order in which you're adding up the numbers in the matrix. So you'll see these kinds of things in collective communication, as I mentioned before. We'll see reductions come up a lot in message passing, where you have a bunch of independent processors. And for example, the standard message passing library that most people use, and that you'll be using this class, is MPI, and that assumes associativity of the reductions. What does that mean, it assumes it? It means that it will reorder things under the assumption things are associative, and you can do it on floating point arithmetic, but you should be aware that you may not get the same answers you would get in a serial code. So find Spark, it turns out, and this was something that I think some of Jim's students discovered a few years ago, assumes both associativity and commutativity. And that is a little bit of a problem, because we're going to see some examples later where we're not just using scalar values. So it's not just a floating point problem. That floating point is also not commutative, because you can have sort of different size registers, and one value can be in one register. Exactly how they get added together can also give you different results under floating point. But if you're doing it on matrices, matrix multiply is not commutative, so you can actually just get the wrong answer. So this means that you can't use matrix-based reductions, so that is where you're doing a matrix multiply as your reduction operator if you're using Spark. And I think they haven't fixed this, right, Jim, as far as you know?
It's a feature, not a bug.
It's a feature, not a bug. Okay. It runs even faster. It just doesn't get the right answer. Okay. Well, it depends on what you mean by the right answer, right? So, I mean, it does get the same kind of answer that you get, but assuming associativity and commutativity. And so that is it's specified that way, but it means that you can't use certain algorithms. Okay. Let's see. The reductions can go even faster than the, so in terms of the, how long, can we make the reductions go any faster? Sorry, this is about, what is the lower bound? Could we make a reduction that was faster than log n? So let's try to argue that you can't actually make a reduction go any faster than log n. Well, the reduction is a function of all the variables in the array, the n variables, input variables in x1 up to xn that are in the array. And so in in order to make this lower bound argument, what we say is, well, if we have only binary operators and we're trying to compute something like a sum or whatever, but any binary operator that or any reduction that we're going to use with a binary operator, well, at the first time step, each of the outputs can only depend on two input variables. So it's really that bottom of the tree, and then using induction, after k time steps, an output can only depend on 2 to the k inputs. And so after log 2 input time steps, the output depends on at most n input variables. So what does that say? That says that we can't possibly do better than log n in a reduction, and which is kind of nice to know. It says that we've got a tight bound on our cost of reductions. We can implement a tree with an unbounded number of processors, if we have that, in a number of processors that's equal to the size of the array. We can get a log n time algorithm in parallel. But it also says we can't do any better than that even in parallel. There's no sort of magical way, because you can't add up all the elements of an array and not use one of the elements in the input, right? You have to look at all the elements of the input in order to have a value that is computed on all the values of all the quantities in the input. You have to at least look at every one of them, and with binary operators, that'll take log n steps. Okay, and as I said, the binary tree actually performs this kind of computation. Okay, so here's a cute little way of thinking about matrix multiply. Jim talked a little bit about this last time, but I think we'll talk more about it when he does the parallel dense linear algebra lecture. But let's assume we're multiplying these matrices. We'll assume they're n by n just for simplicity. And so what are we doing? Well, we have in our normal nested loops, we have I, j, and k, right? You've seen this a lot now. And so we've got those 3 loop nests. We'll assume that we actually have n cubed processors. So that's a lot of processors, right? This is in the kind of crazy unbounded world in which we can just put a processor at every one of those points in the matrix. Then there's 2 basic steps in the parallel algorithm. The first step says I'm going to just multiply one value of A and one value of B to give me one value that's in the interior of that whole domain. It's one of the multiplies. Every processor does one in parallel. It happens in constant time, right? So on n cubed processors. And then I have to add them together in order to get each value of C. That's going to be something that's logarithmic in the depth of that dimension n of the matrix. So I can do that in log n time. And so you're going to see that this idea actually does come up in a useful parallel algorithm called 2.5D matrix multiply. And I'm not going to try to describe it here, because I know Jim will talk a lot more about it when he does the dense linear algebra one. But you can think of it as kind of coarsening this is kind of silly parallel algorithm where we've got a ridiculous number of processors, n cubed processors, into chunks of that iteration space and putting a processor inside of each one of those chunks. And then each one of those processors will do one of the pieces of the computation in that chunk. And then after they're done, the processors that own some kind of column of chunks are going to add them together in order to get the C matrix. Okay. So that gives you an idea of why you might study these parallel algorithms, because even though the algorithm itself, something that uses n cubed processors, is not practical, it can give you some intuition about a practical and very efficient algorithm. And here I'm not talking about communication costs, but that's something that it turns out that this is very efficient from a communication standpoint as well. Okay, so that's a little bit about how we map reductions onto parallel machines, and as well as the sort of trivial computations onto parallel machines and something that you can do with them, such as matrix multiply. And next I'm going to talk about parallel prefix. Any questions before I go on? Okay, so these will be the most interesting of the algorithms. So remember, we talked about this scan operation, and the scan is going to take a binary associative operator, and it's going to produce this list of values as the output, which is a reduction that goes kind of up to that point in the array. So there's the add scan value, and you can do it on real number, plus and times, min and max on reals, as well as booleans, or actually on matrices using matrix multiplication, all of which are associative modulo the floating point issues that I mentioned before. So how do we parallelize the scan? We had a question a little while ago about that, and yes, it does seem not completely obvious how we're going to parallelize this thing. So really it looks like this, that if you wrote down the code for it, it says that you assign the first value to 0 in the exclusive case, and you then y sub I going from 1 up to n is going to be equal to the previous value plus the input value at that location. So that takes n plus 1 operations, adds, so it's but it also runs in parallel time that is order n, right? Because it's a serial implementation, and it looks kind of like it's impossible to parallelize. So what are we going to do? Well, to think about this, remember that our operations are associative. So if our input array is there, just the numbers 1 through 8, and our output array then is the scan, the sum scan of those, is there some point that we could see of adding up 5, 6, 7, and 8? Well, that's a useful value, right? For not just for location 8, but for locations, or let's say 4, 5, and 6 are going to be useful for the locations that are at 6 and at 7 and 8. So some of these partial sums are going to be useful for other values, and even the value of 5 plus 6 plus 7 plus 8, if we've got that value, we could then compute 5, 6, 7 by subtracting 8 from it. So there's a number of different ways you can use those, but we're going to just by looking at these partial sums. So if we separately have 1, 2, 3, 4, and we also have 5, 6, 7, 8, and then we recursively have the sum of 1 plus 2 and the sum of 3 plus 4 pairwise. What can we do with that? Well, this is what the parallel algorithm looks like for computing scans, and we're just going to do this on an array that contains the numbers 1 through 16, just for simplicity. But the algorithm would work on any. It doesn't depend on the values that are in the array. It just is a little bit easier to track what's going on if we take that sort of simple array, which is the numbers 1 through 16. So the first thing we'll do is to add pairs of numbers together. So we'll get the sum of that we see here. So just the pairwise sum of each thing. Then we will recursively just assume that we have a way of computing a parallel prefix sum. And so we're going to, we'll take the parallel prefix sum, and then you can see the prefix sum on those values. So half as many values as we started from in the input is going to give us 3, 10, 21, 36, and so on by just doing the add sum on those. And then what are we going to do in order to compute the output? So we've done a recursive step, which is itself non-trivial. It'll decompose into other steps. But assuming that we've got that, then we're going to just sort of take some of the values and pass them on to the output. That is, the 3, the 10, the 21 are actually going to be the right results for those particular locations in the output array, right? Because those are the partial sums going all the way up to that point. But now how do we get the values in between there? Well, we're going to add those onto one of the input values that we started with. So for example, we'll take, the 1 will just get passed down as a 1. We'll take the 3 that's up above and add that onto the 3 that's down below. So this 3 up here gets added onto this 3 here in this little V-shaped thing, and that gives us the 6. And similarly, this 10 gets added to the 5 and gives us 15, and so on. Okay, so that's the kind of the easiest intuition behind how we're going to parallelize these recursive sums. And note that it didn't really depend on the fact that it was a sum. It could be done in any operator. All we're doing is we're assuming that we have the ability to do a recursive step where we can compute the scan of the every other element, an array that is half the size, and that will cause the recursion then to terminate, because we'll get down to a single element, and then we can easily terminate the recursion. Okay, so questions about how that works, first of all? Okay. So what's the cost of this? Well, the first thing is just these pairwise sums. And those can be done with our unbounded number of processors completely independently, so that'll take constant time. And then we have to do the recursive parallel prefix call, and then do the pairwise sums, which are adding up the odd, getting the updates for the odd values that are coming out in the end. So the time it's going to take, T1 is showing the total amount of work that you're doing here, which is you're doing n/2 additions in the first step, n/2 additions at the end in order to compute these last values, and then whatever it takes to solve a problem, the amount of work it takes to solve a problem on n/2 processors, on an array of size n/2, and so that's going to give us n plus this t of n/2, which gives us 2n minus 1. Okay, so that's the amount of work we're doing. So now you should think about how that compares to the serial algorithm, right? This is actually, the serial algorithm is just going to take the first value, add it to the second value, store the first value in the first output, then add the second value, and then put that in the output, and so on. So this is doing actually twice as much work as that serial algorithm is. And T1 here refers to how much does it take to run this particular algorithm on one processor, and running this on one processor, which is the total amount of computation you're doing, is going to be 2n minus 1. On the other hand, if we've got an infinite number of processors, and so we've got an unbounded parallel machine, then T infinity is going to be 2 log n because of the recursion in here. And so if we can do each one of these steps in constant time, and there's going to be just a logarithmic number of steps, then we can do the total amount of work in parallel time. So it's a much more parallel algorithm than the serial one. It does twice as much work in terms of computation. We may or may not actually care about that very much, but in terms of, because for a large problem, that factor of 2 may not matter, but we're also, but we are adding to the amount of parallel work we're doing. So there is a non-recursive way of implementing this, and it has both an up sweep and a down sweep, and we probably won't do this in excruciating detail, but we'll look at sort of how this is. It's sort of working in basically the same ways. Oops, sorry, which is, we're going to just update every other element and pass one of the elements on. So this is giving you the sum of 0 and 1 position, so x0 and x1 into this, and x2 and x3 into that position, and so on. And sorry. And then we're going to jump not by just 1, but by 2 locations and add some more things together. And so this will give us the value of x0 up through x3. And this one gives us over here the value of x4 through x7. And then at the end, we'll jump by 4, and we'll get to the value of x0. We'll get the total the reduction operation of the total array up here in the right-hand element of the array. So now we've got some of the pieces that we need for the answer, although we don't have all of them. We've got kind of every other one of them is filled in with what you need, right? Each one of these is going from 0 to 1, 0 to 3, 4 to 5, and then 0 up to 7. Okay, so then that's called the up sweep, and so that's one pass up the tree, and then we're going to go sort of a down sweep where I'm just copying that array, and I know it's a little hard to see the subscripts, but that's just the same array that we're copying here, so we can just watch how it unfolds. I'm going to first of all overwrite this last thing with a 0, and then I'm going to start doing swap operations that are doing some additions and then just some swaps. So we move the 0 over here by 4 places, so it jumps by 4 places, and the thing that was over in that place gets swapped over here. And similarly, we're going to swap the 0 then over into this position and move the x1 over into that position. The sum of x0 and x1 to that position, and then we're going to do the swaps here, and what we'll end up with is 0, and then x0. This is the exclusive scan, and so on. And this algorithm, in addition to being work efficient, so it actually is only doing order n flops, not 2n flops. I shouldn't say order, but it's not doing twice as many flops. But it's also space efficient. That is, you can do it by overwriting the array, which the other one was using really a copy of the array every time you went down the recursive step. And so it's both work efficient and space efficient. Okay. All right, a little bit about real hardware and what real hardware looks like today. So first of all, what you do see on some real machines are, or at least there was a period of time when we were teaching this class when there were vector machines that were still in use. And these vector instructions looked kind of like these data parallel operations. So you could load a chunk of values, and you've seen this in the SIMD world, but these were longer vector registers, so they might hold a set of 64 elements, for example. You can load 64 elements of an array into one of these vector registers and add it to another 64 element array using a single vector add operation. And the number of elements that are in these vector arrays, these vector registers, were often longer than the amount of hardware that you have. This is one of the things they have not done in the SIMD instruction sets, which is a little bit of a problem. This is why every couple of years you hear a new version of SSE or AVX or whatever come out, because they make the vectors wider, and then they have to redo the instruction set. And so back in the vector supercomputing days, what they did is say, well, we are not quite sure how much hardware we're going to be able to afford to put in the next machine, so we'll just assume the instruction set says, let me load in 64 values, and when you do the add, if you only have 4 adders, we'll just take off 4 of those at a time and actually execute those. So those were called pipes or lanes. It might be on the order of 2 or 4 pipes or lanes, but the number of elements in your vector register could be 32 or 64. And part of the problem, I think, on the SIMD machines is they don't want to waste that much or use that much space for the width of the vector registers if you don't have that much hardware that can actually execute on them in parallel. And so these vector instructions would sort of virtualize the amount of hardware that was underneath them. Let's see, I think they were just doing pairwise operations and doing it in chunks, which is equal to the number of pipes or the number of lanes. They're just synonyms. So there's a couple pictures of of Cray machines. There's the Cray X1, and these were what doesn't sound maybe so impressive today, but at the time was pretty impressive, 12.8 gigaflop per second vector processor, and then they would have 4 processors and nodes sharing up to 64 gigabytes of memory, which also was a large amount of memory at the time. And so this was, and then in this machine you could also do remote memory operations in between the different nodes. So we had these vector machines, as I said, for a while, and the older SIMD machines, that kind of idealized model, also was around for a while, but then these vector machines were really taken over by the massively parallel machines, so that you have in a system like Cori. And so you've got vector architectures that are based on this single processor model that has this multiple functional units all performing the same operation. So it's a nice sort of abstract machine model in the vector, and they were important to understand the history of the architectures, and they do come back from time to time. So and they are coming back now in both SIMD instruction sets and GPUs. Although exactly what functionality you have, so remember I mentioned scatter gather, that's something that you typically have not been able to get in SIMD instructions. I think it does exist in AVX 512, but the set of functions that you had in these vector supercomputers was actually more powerful than what you tend to get on the SIMD instructions today, and I think the GPUs are also trying, in some sense, to catch up with that power, although the challenge is you can imagine that implementing a scatter gather in hardware is very expensive because you've got to shuffle all this memory around, and you don't want to slow down the whole processor just for that operation. Sorry, keep hitting the wrong one here. Okay, so, and then what about on distributed memory machines? Well, we can, we typically do not have machines made out of little tiny processors where we can put 1 per element of the array. We're going to have much more powerful processors, and so what we're going to do when we map these onto that is put a chunk of data parallel work on each one of them, and within each one of those processors it'll run the algorithm serially. So you need to map the n-way parallelism of your data parallel language or whatever, or your algorithm that you're thinking about in your head, to p-way parallelism that you have, where n is typically much larger than p. N, the size of the array, is much larger than the number of processors. This was something that in the high-performance Fortran era, HPF, they tried to do this automatically or semi-automatically. They kind of gave up quickly on doing it fully automatically. They knew that would be too hard. They were trying to do it on these massively parallel cluster machines of the kind that we still have today in systems like Cori. And there was a lot of effort in trying to automate this. It's not clear, frankly, whether the community gave up before the compiler people were able to get something useful out of it, but in any case, they did give up on trying to do this automatically. And so today, people typically write message passing code, not this kind of pure data parallel code on these massively parallel machines. But the ideas will come up in everything from cloud computing, as I said, to collective communication. So if we're mapping data parallelism onto clusters, if we've just got our simple binary or unary operators, it's pretty straightforward to see how you're going to map them. You're going to just take a chunk of the elements of A, a chunk of the elements of B, and put those on, and C, and put those all on one processor. And so the cost in this case is going to be N over P. And you can't do much better than that, where if P is actually equal to N, you get back your constant time speed up. But in practice, P is not going to be equal to N, and so you'll get a cost of N over P, and a speed above P. And then if the arrays are not aligned, then you're going to have to do some amount of communication. So that is another thing that we'll worry about a lot when we start talking about these distributed memory algorithms. And then what about the reductions and the broadcasts? Well, if we got our elements distributed across the processors, where each processor has a chunk of, say, 5 elements each, what is the cost of doing the reduction? Well, it's N over P, the cost of that to add up the things locally, right? So if you've got your 5 elements, that's 5, N over P is equal to 5. It's going to take you order 5 arithmetic operations to add those up, 4, but anyway. And then you have to do the reduction through the network, but that's not order log n, it's order log p, and p is much smaller. So you're going to do a tree reduction or a tree broadcast. It's sort of the same way. You can do a tree broadcast to each processor and then copy on the individual processor out to all the elements if you really want that element replicated in all of the elements of an array. Okay, so any questions? What about parallel prefix costs? Well, they really can be done in some sense in the same way. We're going to compute the local parallel prefix and N over P steps, and then we're going to run the parallel algorithm in order to get the updates across the processors and use that to then update to compute the values that you need in order to update your local copy. So you can think of it this way. You'll get, if this processor, you compute a parallel prefix, you send your rightmost value sort of up through this scan tree in order to get the results. What you'll get back is what is the sum of everything to your left, and you've passed on what was your own sum to somebody off to your right, and then you use that to add that to everything in your own local array, and that will give you the prefix sum of everything that's in your processor. So what is the time for this? It's just the serial time in each processor, which is again order N over P, and it's plus the time to do the prefix scan. And I don't have the constants in here in this particular case, but notice this is the time on on P processors, not the time on an infinite number of processors as we had before, or the time on one processor, which was the total amount of work that is performed. And so on P processors, it takes time N over P for the serial work plus the kind of the embarrassingly parallel part, if you will, and then log P for the part that has to happen using the parallel algorithm, the reduction algorithm, the parallel prefix algorithm. So I think the myth of log n, as Alan Edelman likes to call it, is that the log2 span, or log n span of the parallel algorithm that runs on an infinite number of processors is really not the main reason that we care about using things like parallel prefix. The real reason we care about things like parallel prefix is because most of the time is that N over P term, which speeds up perfectly linearly, right? At least ignoring communication and things for a minute. So for example, imagine that you've got a problem N that has 1 million elements per processor. So K, it's K times P, where is the size of the input array, and K is equal to 1 million. Well, what are you going to do in this parallel prefix? You're going to do K adds, or K minus 1 adds at the beginning, and then you're going to do your log 2 P steps in the middle, and then do K adds at the end. And so this is really going to be, these two terms at the beginning and end will really dominate the cost of this. And so, and those are speeding up linearly. If you ignore that middle term, then your parallel prefix just sped up from an order, from something that in serial would have taken you order n time into something that is now n over p time. And so you're going to get you get perfect parallelism from that algorithm, at least in theory. And so that is the key to actually mapping these kinds of data parallel algorithms onto cluster machines, shared memory multiprocessors with threads, or massively parallel machines. And what it means is that you're going to try to use things like parallel reduction operations when you can, but really think of those, the cost of that, even though you might have had the intuition that this algorithm can be run on an infinite number of processors, it will run, you know, much faster, like in log n time, but what you'll get is something that actually runs closer to n over p time or something. Okay, so why do I say it's an elegant programming model? It really has a strict serial semantics to it, so there's really no difference between executing A plus B one element at a time or in parallel. And so you can just think of it as these set of array operations. And for those of you who have written a lot of MATLAB code, for example, that'll give you a lot of intuition about how you want to write some of these kinds of data parallel algorithms. And that the reductions also preserve the serial semantics up to associativity, so as long as you really have associative operators. And we talked about that in more detail earlier in terms of what can go wrong, but that really says that for the most part I can think of my, say, MATLAB code as the code that I'm executing. I don't have to worry too much about parallelism, whereas already in homework 1, when you're looking at OpenMP, you're worrying a lot about parallelism. So, you know, as I said, the problems are that it's not trivial to map this onto real hardware automatically, for sure, and it's also the case that not every algorithm is going to fit very naturally into a data parallel model. It's a very sort of synchronous model that says every processor takes one step at a time doing exactly the same things. If you get into an algorithmic scenario where you're masking off a lot of processors, and worse, you're kind of masking them off recursively, you're going to be in a situation where you have a very inefficient parallel algorithm because a lot of the processors are sitting there idle. And so you have to have some way of then turning that into an efficient algorithm that will collect all the work together to do at once. So here's a partial list of all the things you can do with these kinds of scan operations in particulars, but data parallel operations in general. So broadcasts and reductions that we talked about in log n time. The parallel prefix scan is in log n time. And then what are some things you can do with them? Well, you can add n-bit numbers, and I'll give a few examples of these depending on how much time I have. You can invert a triangular matrix. You can do some kind of parsing operations. You can do a 2D parallel prefix operation. Actually, that citation there, Brian Catanzaro and Kurt Koitzer. Also, I think there's an old YouTube video of Guy Steele talking about the same algorithm for image segmentation. So you can watch that in the YouTube video if you want to. You can also use it in browsers. Also in the original paper by Steele, Hillis and Steele. So Guy Steele and Danny Hillis. A lot of these algorithms are in there. So I got a reference to that paper later. But some of these are very classical algorithms that have been around for a long time and were inspired by these massively parallel SIMD machines, these machines that really did have just one control processor and were broadcasting instructions out and said, everybody do an add. But now they get rediscovered or reinvented or kind of reused in a certain way on GPUs and on SIMD instruction sets, and even on in massively parallel message passing where you're doing broadcasts and reductions and so on. Okay, so let's do a few of these examples of algorithms that are kind of interesting and maybe non-trivial in terms of how they get parallelized. The first one is stream compression. So what is the idea? That we have an array of values that are coming in. So they're just streaming in. Maybe we're doing some data analysis on it. But we want to pick out a certain subset of the values. So we also have an array of flags. So there's the array of flags and the array of values. And what we want to do is compress them down into this array of subset of the values from the values array into the result array. And so we're just going to compute an exclusive add on I guess we're adding them using the flags. And so then we get this index set. We do an exclusive add scan of the flags. And that gives us the array that you see here, right? So this is just the 0 because we're doing an exclusive sum, and then 0 plus 1 gives us the 1, and sorry, the 1 gives us the 1, and then the 1 plus 0 gives us the second 1, and then 1 plus 1 gives us the 2 there. So that's the add scan of the flags array, just that array of zeros and ones. And then we're going to use this to scatter the values into the result matrix, but masked by the flags. So, you know, we've got duplicate values in that index array. And the example I gave before of writing, like doing a scatter or a gather operation had a permutation. So we only had one location that each one of the values was going to. In this case, if we took that index and we didn't mask it, we'd have multiple values getting written into the same location. And exactly what that would do on a particular programming language or particular hardware is not entirely clear. They would define it in a certain way or say it was an error or whatever. But in this case, if we mask it by the flags, then we only have one value that's coming from this original values array and being written into each location. So this one's going to be written into location 0. The 4 will be written into location 1. That's right above it. The 1 will be written into location 2. And the 3 will be written into location 3. And the 1 will be written into location 4. So, that's how the compression happens. Okay, so the next example we'll do is sorting. And we actually used this algorithm a number of years ago on a machine called VIRAM, which was a vector processor. And these algorithms, I said, can be inspiring for how you're going to map something onto some piece of parallel hardware, whether it's a GPU or SIMD units or some other kind of vector processor. Or even a distributed memory processor. So here's a radix sort, and for those of you who are not familiar with radix sort, I'm just going to describe radix sort first, and then we'll talk about how it gets parallelized. So it's a little bit counterintuitive, because what we're going to do is sort of sort by the least significant bit first, and then sort by each other bit in the input string until we end up with everything being fully sorted. So what's the first step? The least significant bit, so I'm just writing out these bits as, you know, a bit 2, 1, and then 0 in that order. So the least significant bit says, well, really I'm going to look at the last bit of these numbers that each have can be encoded in 3 bits here, and I'm going to end up sorting based on that last bit, meaning I'm going to put all the zeros to the left and all the zeros to the right. Okay, so that's what this array has. It's taken all of the things that are evens and put them on the left, and all the things that are odds and put them on the right. Next, I'm going to sort on the next bit, sort of doing the same thing. Now I'm going to do a stable sort. And what a stable sort means is I guarantee that I will not rearrange anything that doesn't have to be rearranged because of the bit that I'm sorting on. So I'm going to keep everything in the order that it was in the original array, but just move the things relative to each other if they have to be moved relative to each other. So for example, I'm going to sort it on the next bit. I'm going to look at all of the things that have, you know, so anything that has a 0 in the sort of the 2's location, if you will, is going to get put on the left, and anything that has a 1 in the 2's location is going to get put on the right. But notice that I kept, you know, 4 and 0 and 5 and 1 in the same order that they were in from the original even-odd sort. And the next then would be to stably sort on the next bit, and so this would be looking at things that are, you know, less than 4 are going to go to the things that are greater than 4. And so indeed I end up with a sorted array in this case, but that's partly because again, when I'm doing a stable sort, I keep the blue elements all in order, relative order to each other, and I keep the white ones all in order relative to each other. Any questions about radix sort first? I know many of you have seen this many times. Other people might not have. Okay, so how are we going to do something like this in parallel? Well, given our input matrix, the first thing we'll do is compute an array of bits, which is basically just the last bit of each one of the elements. Okay, so if it's an odd, it's going to get a 1. If it's an even, it's going to get a 0. And then I'm going to compute the complement of that, which is the evens, which I could do directly or by just complementing the odds array. And so that says that the last bit is a 0. And then I'm going to do an exclusive sum that scans this sum scan of the evens array. And so that is this blue, with the white and blue one here, with an exclusive sum scan. And I'm going to keep this last value, which kind of falls off the end, if you will, of the sum scan, which I can get out of it. And then I'm going to broadcast that out to another array. That is giving me the total number of even values, right? So, I did happen to start with the arrays 0 through 7, and so there's 4 even values and 4 odd values, and so there's 4 total evens in here. And then I'm going to just make up an index array, which is just the numbers sorted order, 1 through 7, 0 through 7. This is unrelated to the input values. The input values, maybe I should have made them floating point numbers, but they get kind of ugly looking. But anyway, they could have been other numbers there in the input matrix. So this is just the values of the indices 0 through 7 integers. And then what I'm going to do is compute this kind of funny thing, which is the odd position. And this is the position in which I'm going to place all the odd elements. So think of that as the kind of like that array compression thing. I'm going to calculate for each element where it's supposed to land in the output array. And so I'll say, well, in the odd position is going to be, and this is just giving me that first step of the radix sort. I'm just trying to get all the evens to the left and all of the odds to the right, okay? And so the odd position is going to give me the total evens, right? Because I want to put everything up to the top of all the evens, plus the index value minus this even pos thing, which was this exclusive sum of the evens, and this is going to give me the position that I'll put them in. And so then the position is, if the actual position is going to give the either something from the evens array or something from this odd positions array. And then we're going to scatter things out using that position as the index for that. And lo and behold, we'll get the evens on the left and the odds on the right, which was what we wanted for the first step of radix sort. And now I won't go through and walk through the next steps, but hopefully it's clear that if you do the same thing, but not on the last bit, but on the next bit over, you can do the sorting in parallel. So you can do the sorting here as well. And each one of these operations is something that you can do in data parallel in either constant time or logarithmic time. So the whole algorithm ends up being a log n algorithm, and is actually a practical parallel algorithm. So, okay, so that was radix sort. The next one is actually something that happens in hardware. So imagine that we're trying to add together 2 n-bit binary numbers, A and B. So I'm just going to write A as the bit A sub n minus 1 down to bit A0, and write B as bit n sub B n minus 1 down to B0. And I'm going to compute the sum of A plus B. So these are just 2 numbers, right? I'm just computing the sum of 2 numbers and putting it into, but you can think of each of those numbers as an array of bits, and the output is going to be another array of bits. And I'm going to use another temporary, a couple of temporaries, but one is going to be called the carry bit, which is what, just think of it as, you were taught to do addition back in, 2nd grade or 1st grade or whatever, kindergarten, and they said, oh, well, if you're adding together a big number, then you need to carry the bits over. So you need to carry the numbers over. In this case, we're going to be doing a binary arithmetic, so we'll just be carrying a 1 or a 0 over. And so the formula is that the rightmost carry bit to compute that carry field is always going to be 0. So that's something way off to the right. And then for all of the other, then to fill in all the other elements of both the output, the sum array of bits, and the carry bits, where say S sub I is equal to the XOR of those 2 AI and BI positions, as well as the XOR of the carry bit that's to your right. And then you're going to compute the carry bit for this particular location by computing the XOR with an AND of the carry bit and the AI and BI. So let's see, can I give some intuition for this? This first statement, the sum, says that either one of these things is a 1 or 3 of these things are a 1, right? I've got an odd number of 1s, and then the sum is going to be a 1. Either the carry is a 1, or the A is a 1, or the B is a 1, and then I'll get a 1 on the output. And if only 2 of those things, if 0 of them are 1s or 2 of those things are 1s, then I'll get get a 0 in that position. But instead, I'll set the carry bit to be a 1 if 2 or more of them are 1s. And that's what this formula is doing. And this is, I guess, just the point is these are all formulas that can be done. They're associative operators, an exclusive OR, an AND, and a regular OR, and so they can be done using these scans and things like that. So here's a little example of how this goes if we've got these two binary numbers. So we've got the number 22 and the number 29 written in binary, and we're trying to compute the sum of those, C. Which is, the sum is S, which is going to be 51, and there's our carry bit array. So how would we fill it in? Well, the first thing we do is we fill in that rightmost element with a 0, and then we compute the sum at that location, which is really the first step in the assignment statement in the loop. That gives us a 1 because there's an odd number of 1s in there. And then we can also compute the carry bit for that same location, which is a 0 because it was only 1 1, there weren't 3 1s or something. And so then we just can continue doing it that way and computing the result, and what we end up with is the value 51, which is what we want. Okay, so now the point of this is, can we do all of this in log n time using a parallel prefix operation? And so the answer is yes, we can actually do this in log n time using parallel prefix. And so what's the idea behind this? Well, we'll just start by setting the rightmost carry bit, and then the next carry bits here are computed using this formula. So the carry bits are computed with the XOR AND that I showed you before, and then we're going to compute the CIs in logarithmic time via the parallel reduction, but I'm going to compute two other temporary arrays, which is the propagate bit. That's really when things are coming over, sort of being, let's see, when just the A and the B are going to generate an extra value that has to be added, or and then the generate bit. And these can be done both in order 1 time on n processors, if you have a processor at every one of the bits. So now we've got a really crazy machine that's got a single processor at every one of the bits. But you can then turn this into a little matrix operation, little matrix operation here, which says that the carry bit at location I is equal to this formula, which is the formula that I have up here for it, which is we're taking the propagate bit, right, which was AI plus or BI, which is up here. So this is the propagate bit part, and then I'm going to get the generate bit part, which is going to be used over here. That's the OR part of it is the generate bit over here. And so I can write this formula down as a little matrix operation, and then compute this as a little 2x2 matrix multiply times the input matrix, and just write that little matrix as M sub I. And now I get a nice sort of formula that shows how I'm going to use the parallel prefix on the matrix multiply operations, Mi up to M0 times this input vector 0, 1. And so by doing we can do parallel prefix on these little 2x2 matrix multiplies, and that are Boolean matrix multiplies, and that's an associative operator, so we can do these in parallel and get exactly the right answer, and so on. And this is actually used in carry look-ahead adders in all hardware today, and was even in the original Babbage difference machine. And so going back to how they did addition in there to make it fast, this is used down in the hardware. So you don't need to write these algorithms, fortunately, but it does give you some idea of how these kinds of data parallel algorithms are useful. So the last class of algorithms I'm going to talk about really come from segmented scans. So these are just like the other scans, but we're going to compute them in chunks. So in this case, we're going to have our value array and some kind of a flag array, and we're going to just not do a scan all the way through, but do it in chunks based on wherever the flags are. So for example, if we've got this flag with 1s in these 3 locations, we'll have the first segment be be the 1 and 2, and the second segment be these pink things, and the next segment be blue things. So we're doing a sum scan on them, but only up within the boundary that you have written here. And there's different ways in different languages and so on that you can designate these flags. They could either be done as a list of values, or they could be done as these list of bits, or with true, false values, or whatever. And so the result of doing this is, if you've just got the first 8 numbers, 1 through 8 here, then we're doing the sum scan, the segmented scan. We add the first 2 together, so that gives us for the inclusive scan, we get the 1, and then the 1 plus 2 for the 3. We get the 3 here, we get the 6 there, and we get the 8 there, and so on. You get the partial scans for the sum scans for the different pieces. So why is this useful? Well, I think Jim talked about sparse matrix vector multiply a little bit last time in the sparse compressed sparse row format. And so if we've got a sparse matrix, we don't want to store all the zeros in the matrix. So what we'll do instead is just take all the non-zeros, pack them together in a contiguous array, and we'll call that the values array, val. And then we'll have another array index that tells us which column that non-zero is stored in this matrix on the left, which we're not going to actually build, right? That's just the picture of what it would look like if we filled in all the zeros. And then we have a pointer array that tells us where the beginning of each one of the different rows of the sparse matrix starts. So there's the red row, the green row, the blue row, and so on. And so there's our matrix multiply kernel. This is what it looks like, and it's got this nice recursion in here. It looks like it might be somewhat serial, but we're going to, of course, take advantage of associativity of the plus operation in here to parallelize it. But we don't want to just add everything together in the value array and say the input vector x, because they don't all correspond to each other. They're not even the right size. But they also, you don't want to just multiply the corresponding elements. So you have to figure out which element of x do you multiply times each one of the non-zeros. And the reason we've written it this way with the result vector y on the side and the x vector here on the top is because you can see then if you look at the index of this non-zero, the second non-zero here, which is stored in this index array right there, you can use that to look up in the x array the particular value that you need to multiply by. So that's where you see this expression x of index of k, which is the particular position you're at running through the value in index array. And so now can we do this using a scan operation? And actually you can do it using, you need a segmented scan to do this because these things are packed out, and you basically need to keep the rows of the sparse matrix separate from one another. And so here we've got the input vector, we've got our pointers that says where the rows each start, and then we've got our index array and our value array. So these are all the inputs, right? That's our sparse matrix input A, which has these 3 things, and our input vector x that we're going to multiply a times. And so then we're going to compute a flag vector. So this flag vector is just used by computing taking the zeros vector, so something that's the right length of zeros, and then and it's going to then add a ones vector, but masked by pointer, and so indexed by pointer. So it's going to take those index locations where the pointer said they start, and then put the non-zeros into those locations. And then the product is going to be we're going to get a product for every one of the elements that we need in the matrix, and by multiplying the value of that each one of those values inside of this value matrix times whatever value at x is stored at the corresponding index. So looking them up in here, so that gather operation, and then we do a sum on them. But the trick is that we want to only add up the rows. So the sum scan is going to give us the sum of each one of the rows separately from all of the other rows. And so we're segmenting it by this flags array that we computed earlier. And the other kind of trick in here, just to make the code a little bit easier to write, is we're going to use a suffix scan instead of a prefix scan. That means it does it in the opposite order. And so the sum of the values actually ends up in the leftmost element of the segment of the array, not the rightmost element. The other examples I've given, we've always been putting the maximum sum in the rightmost element. It's rightmost on that side, but here it's ending up to the left, and that just makes it easy then to write the actual answer of product out. Y is equal to the sums of the pointers. So you're just going to pull these bold-faced things out of the sums array, and that will give you your result vector. Okay, so let's see. I can also compute Fibonacci numbers. So there's a nice recurrence for computing the n plus first Fibonacci number as the sum of the n minus first plus the nth Fibonacci number. I can write that as a little matrix recurrence like this, and then I can compute all of the fn Fibonacci numbers by doing a matrix multiply prefix on this thing. So we're now our prefix operator is a matrix multiply, and just because of this recurrence, it will gives us this property that we're going to get the Fibonacci numbers out of this. And then if we just want the nth one, we can select the upper left one that comes out of this. So a couple of other non-obvious things you can do with these kinds of operations. One of them is pointer doubling, and the example here is what's called list ranking. So what is the idea? So I've got a linked list, and it seems like there's nothing kind of more inherently serial than trying to walk around at a linked list. And by the way, this is going to be somewhat related to the homework assignment you'll do for homework 3 when you're looking at a genomics application. You're going to be trying to walk through a graph, which really is kind of a graph of linear links in it. And so what is the idea? Well, we're trying to compute, this is just a simple case. All we're trying to do is compute the ranking of the elements of the list, which says what is the distance between this element in the list to the end of the list. So what's the difference between me and the end? That seems like something that would be pretty serial. I'd just have to walk through the list, starting at the beginning, and then, or even starting from my own location, and walk forward until I hit the end of the list, and then I would know how far I am from the end of the list. So it seems like a serial operation. Indeed, this recurrence is just giving you the definition that looks pretty serial. So now, what do I do with this? Well, I'm going to assume that there's a processor sitting at every one of the nodes of the linked list, and it somehow can find that node of the linked list. And it's going to then do what's called pointer doubling. So it's going to replace at each step, it's going to run a series of steps, and at each step it's going to replace, first of all, it's going to put ones into every element of the linked list. So there may be some other values in here, but we're going to have a little place that we can just put a 1 in there so that we can have a value to keep track of what the rank of this particular cell in the linked list is. And by the way, I've drawn it in the easiest possible way where the linked list is laid out in kind of memory or across processors in what looks like an obvious order, but they could be all scrambled around, right? The processors could be pointing to linked lists on nodes on other processors and so on, and the algorithm would still work. But I tried drawing it, and it gets crazy. So now with this nice list, we've got a list of ones, and then in the first iteration, what we do is we replace our next pointer with the next pointer. So we just take the thing that it used to point, that you pointed to before, and replace it by the thing that it pointed to. And you also increment, you add together the value at that other one at the next, that next linked list node, which everything is a 1. So in the first step, you add the 1 in that guy's node to yourself, and you get a 2. So everybody gets a 2, and everybody gets a pointer that's 2 hops away instead of 1 hop away. And then in the next step, you get pointers that are 4 hops away, and you're adding up, you're getting 4s in many of the locations. The exception is near the end of the linked list, and I guess that happened even in that first iteration. If you were already at the end of the list, you don't increment, you don't add the values together, because you already know how far you are from the end of the list. And you also know that you don't need to do anything with your pointers because you've already hit a null. You've already hit the end of the linked list. And so I should have pointed out that the very last value in the initial linked list is also a 0, and that's got a null in it. And you keep doing this until basically you run out of next pointers to have to traverse. Everything ends up with a null pointer after you've done 4 iterations here. And you can do this in logarithmic time. So also sort of a non-obvious thing that you can do. You won't really be doing, I think, this kind of logarithmic algorithm, but it is, you are going to be walking around linked list type things. And probably one I won't really have time to describe in detail because we've just got a couple minutes left is if you're doing lexical analysis, but I like it because it's non-obvious in terms of what you actually have to do. So in lexical analysis, we're trying to take a string of characters and turn it into a set of tokens. And So in these tokens, for example, if we have a little language that has identifiers, which are just strings of characters, and we have strings that are in double quotes, and then we have our arithmetic operations, which are plus, minus, times, less than, and so on, and then we've got sort of general expressions. We're going to build a little finite state machine, and if anybody's written a compiler or in a computer science kind of class, you have probably seen something like this. What it says is that if I've seen a string, and I see, if I'm in the middle of a string and I've seen anything but a closing quote, then I'm still in the middle of a string. And if I'm in any kind of an expression and I see an opening quote, or actually there's just one quote in this particular language, I'm assuming then I'm now in the middle of a string. And similarly, if I am in kind of any place I start, if I'm in an expression and I see an equal sign, that means I'm in the middle of an arithmetic operator, and so on. And so this finite state machine just tells you how you, what kind of state you're in when you're trying to parse the input. But you can write it, and this is not the complete finite state machine because it was kind of messy, but this is the complete state machine, which is actually this matrix. And then it turns out that you can look at each one of, you can parallelize this operation, which seems like an inherently serial thing that is walking through the finite state machine. And without going through all of the details here, just look at the fact that in this table, so I'm now trying to parse this particular input, IF space X space so on. I can parse the right-hand side of it without knowing what's on the left. Not completely, but I can get a lot of information that says, well, if I've seen whatever state I'm in, whether I'm in NA, Z, these are the different states of the finite state machine, I know the next state I'm going to be in based on the fact that I've seen a less than sign and then an equal sign and so on. And I can turn this, kind of compress that set of things by looking at the set of states you'll go through and end up in this set of states A and then S. And so that is also an associative operator, and so you can now do scanning and this kind of walking through a finite state machine in logarithmic time. So just to summarize, sequential semantics are really nice. You don't have to worry about race conditions and a lot of other things that come up. Debugging is a lot easier. It's a lot easier to reason about these kinds of programs. The cost model is really kind of independent of the number of processors. It's about the inherent amount of parallelism when we do a lot of that asymptotic analysis. In practice, you're going to need to take these algorithms and map them onto a finite number of processors. And there's some great classic reading in here, including the paper by Hillis and Steele, as well as a YouTube video by Guy Steele from, I think it was 1990, that you can find there. And then Guy Blelek has a language called Nestle, which is really a nested data parallelism. It's a little bit more general than what I talked about here. Think segment and scans, but even more general than that, but also has some really nice algorithms in it. So any questions? OK, thanks very much.
It was just about this one thing. I wasn't sure how the